All right, we're going to go and get started. It's 7:20. I'm giving a few extra minutes for folks to get in. So thank you, sir. Let's take a look and see what's going on. Let me get back on this screen. All right, let's see what's going on. But yeah, things are working better today online. That's wonderful because, man, yesterday was a struggle. Everything was moving slow. Things weren't moving at all. But things seem to be clicking right along today. Okay, let's look at our grade screen as usual. We should be done with Unit 2. We are starting October 26th right here, 3.01. I had 3.02, but getting through all these special products today, this is stuff you probably haven't looked at before with quadratics. Next week, we'll look at factoring by grouping, and I'm not sure. We're not going to do 3 lessons. I guarantee it next week. There's no way. We might be doing 2, but I've got to kind of look at the schedule going forward to see, because we're trying to get this wrapped up by Thanksgiving. I don't want to have the test after Thanksgiving because you don't want to learn all this stuff and then take a week off and then come back and take a test. I want to get the test before Thanksgiving. So there's a lot to cover in this quadratics unit. So we're going to look at 3.01 today. And like I say, you're going to want to take notes because we're going to learn cheat codes, right? Cheat code. Yeah, that's what I'm calling it. There are some shortcuts in mathematics if you recognize the pattern. If you don't recognize it, then you'll do all the hard work and do it the old-fashioned way. But we're going to learn some cheat codes, some shortcuts, quick ways to factor if you can recognize the pattern. So that's what we're going to look at. So, all right, they say Taylor's at it again. You remember the little like 40-year-old girl in the little funky cartoon videos they have there. She's trying to reframe a square photo this time using a square frame. But before reframing it, she needs to find the dimensions. So she said, well, I could get a tape measure or ruler to find the dimensions, but since she's such a math nerd, she thought she'd use the excuse to study for her upcoming math test. So her dad told her the area inside the frame is x squared plus 12x plus 36. It's a quadratic equation for the area inside the frame, where x is the length of each side of the photo. So she needs to know how much longer the frame is on each side than the photo is. So the question becomes, what is the length of the frame in terms of x? Is it x plus 1, like it's 1 inch longer? Is it x plus 2? Is it x plus 3? How much longer is the frame compared to the photo? So after this lesson, we're going to be able to answer these questions. How can a greatest common factor be separated from an expression? What methods can be used to rewrite square trinomials and difference of square binomials as separate factors? And in what conditions can a factored expression be factored further? So first we're going to start off looking at just greatest common factors. That's better. So we're going to look at like the greatest common factors and simplifying and all that kind of stuff. And let's just start back in elementary school when we were working with fractions. That perhaps we had a fraction like this, 8/24. And so when we see something like 8/24, it's like, well, that is an interesting fraction. You may have not seen 8/24 before, but we can simplify 8/24. So if we look at that and go, we need to know the greatest common factor. What is the number that both of these have in common? And you can do that like this, like what are the factors of 8? Right, so 8 you can multiply 1 times 8 and 2 times 4. And that's about it. That's the only numbers we can multiply it. So these are the factors of 8. 1, 8, 2, and 4. With 24, the factors are 1 and 24, or 2 and 12, or 3 and 8, or 4 and 6, right? Because we can multiply 1 times 24, 2 times 12, 3 times. There's a lot of factors of 24. If we want to put them in order, it's 1, 2, 3, 4, 6, 8, 12, 24. And these are 1, 2, 4, and 8. So if we compare those, they both have a 1 in common, but we don't care because dividing by 1 doesn't change anything. They both have a 2 in common. They both have a 4 in common. And they both have an 8 in common. So we want to know the largest number they both have in common, and that would definitely be the 8. 8 is the largest number that is a factor of both numbers. So that means if we go back here, we can divide the top by 8, and we can divide the bottom by 8, which means we're dividing by 8 over 8, which is just 1. So we're not changing what the number equals, but we're dividing this by 8 and that by 8. So 8 divided by 8 is 1. 24 divided by 8 is 3. So this is equivalent to 1/3 just by finding the greatest common factor, right? Very simply, like we did back in elementary school, just figuring out what's the way to simplify this is using the greatest common factor. Well, we're going to do the same thing with polynomials. So let's go back to our lesson. I think we start off with a video here with our first one. So yeah, this shows the whole thing. 8 dividing by 8, top and bottom is 1/3. Well, we do have. All right, so let's talk about factoring with this polynomial right here. All right, let's take a look at factoring this first polynomial.
Ignoring the variables for a moment and looking at each term separately, ask yourself, what is the GCF of 3, 27, and 15? There are at least 2 ways to determine whether or not a group of numbers shares a GCF. You may make a list, or you may create a factor tree. The factor tree factors any composite number into its unique product of prime numbers. Notice that 1 is not included on the factor tree. The greatest factor that all 3 lists and all 3 factor trees have in common is 3. Therefore, a 3 should be factored out of each term. Write the GCF of 3 in front of the trinomial, then divide each term by it. It is not necessary to show the 1 in front of w to the 4th power, since it is understood. Now take a look at the variables in each term. Do the terms have any w's in common? It may help you to see any common variables if they are shown in expanded form. Since the last term is a constant, there isn't a variable that is common among all terms, so the greatest common factor, GCF, must simply be 3. The final factored expression is 3 times the quantity w to the 4th power plus 9w squared plus 5. Be sure to check the factors by distributing the GCF. The factors work because their product is the original polynomial. Now, take a look at what happens when there is a common variable.
Okay, so the first step when we're factoring a quadratic is pulling out a greatest common factor to make it a simpler quadratic. Like, starting with 3w to the 4th, and this is larger than a quadratic because this is just showing how to factor in general. Starting with this large polynomial up here, if we can factor 3 out of it, now it's just a w to the 4th and a 9w squared and a 5. See, that's a simpler factor. So the factors are 3 plus this polynomial. And what he did down at the bottom is just multiply it back together to make sure that it equals what you originally started with. So if it does equal what we started with, these are the correct factors. So we're going to look at this one right here. So I'm going to do it on paper, the next example. I've already written it down over here. So if we have, and we're like, whoa, Mr. Brock, now we've gotten really crazy. We've got 2 variables and all kinds of exponents. 6a to the third b to the fourth plus 9a to the sixth b to the third plus 20a to the fifth b squared. And we want to try to pull out the greatest common factor. So we want to simplify this by breaking out a factor. 6a to the third, b to the fourth, 9a. Here's the whole thing that you just saw on the Buzz lesson. I took it out and looked at the 6, the 9, and the 20. 1, 2, 3, and 6. 1, 3, 3, and 9. 1, 2, 4, 5, 10, 20. That's all the factors. And there's not anything that these three numbers have in common. Like, twos or 6 and 20 have a 2, but 6 and 9 have a 3, but there's nothing that all three of them have. So these coefficients are as simplified as it gets. But let's look at this, and I'm gonna rewrite this in a way that might be a little easier to see what they have in common. So I'm going to start. The 6 just has to stay the 6 because we can't factor anything out. But a to the third is a times a times a, and b to the fourth is a b and a b and a b and a b. So this is the same thing as that, right? This is just a to the third, which means it's a times a times a. B to the fourth, which means it's b times b to b. So let's do the same thing with the other terms. 9, and then we have 6 a's, 4, 5, 6, and it's got 3 b's being multiplied times each other. And then our last term is a 20 with 5 a's and 2 b's. So this is really breaking this out into its factors. The factors of a to the third are 3 a's. A times a times a. That's a third. B to the fourth is 4 b's. So if we look to see what they have in common now, it's like, okay, let's see. They all have an A, right? They all have an A. And if I look, well, they all have another A. So since they all have a second A and they all have a third A, so let's mark another A on there. I don't have any more A's here. I do have here and here, but I have to have all three of them having that. But so I was able to take 3 A's. So when we start writing our factored form, I can pull a to the third out as a greatest common factor because they all have this in common. So it's going to be pulled out. So I'm going to put a parentheses, and this is going to come out to the front. So these are being pulled out. Let's scratch those off. Now let's look at our B's. So there's a B, there's a B, there's a B. Nope, they still have another B. So there's a B, there's a B, there's a B. B, B. Okay, I'm out of B's over here. So they all have 2 B's. So I can pull out B squared. So those get pulled out, those get pulled out, those get pulled out. There's nothing else that they all have in common. This one has some B's. This one has some A's and 1 B. And this one just has some A's. So since all of this is left, we'll write it inside the parentheses. So there's 6, and that's gone, that's gone. B squared, 6b squared is left, plus a 9. Those are gone, those are gone. So I got 3 A's, I got 9a to the third, and I have 1 B left. And then I've got 20, I've got 2 A's left, 20a squared, and no B's. So this is the factored form, greatest common factor pulled out of this. Now, this might further factor, but that's a whole different mess that we're not going to look at right now. It could not. I don't know. But right now, we're just pulling out the greatest common factor. So this is the greatest common factor that all three of these terms had in common. And I want to look at something on here. How did we get from here to here as far as can we do it without having to write all this stuff out? So with that, we're going back to the product property. Remember the product property from earlier where we had if you have x raised to the m power times x raised to the n power, that means you can just add these together. Well, let's look at what we started with and what we ended up with. We started with this term, a to the third, and we pulled out 3. And there's no a's left. Here we had a to the sixth, and we pulled out 3, and so there's 3 left. Here we started with 5, and we pulled out 3, and there's 2 left. See what's happened? We just subtract. 5 minus 3 is 2. 6 minus 3 is 3. 3 minus 3 leaves none. Well, that's just using this in reverse. Like if we have x to the third times x to the fourth, we can add them together and get x to the seventh. So if we have x to the seventh and we take out x to the fourth, we can just subtract 7 minus 4 and get back to what was left, the 3. So it's really the product property we're using to figure out how to take these out, where we wouldn't necessarily have to do this every time. We can just say, I got a 3, a 6, and a 5. So 3, I can pull 3 out of all of them because I know these numbers are bigger. So if I pull 3 out, what's that leave? It leaves 3, it leaves 2. And we'll practice with some of this. We'll do some more problems to get a better feel of how that works. But we're pulling out the greatest common factor. So it goes through these steps here. You can look at it. They say, if we factor it, we can either write the factors like this, 1, 6, 2, 3, 1, 9, 3, 3, or you can make a factor tree, 2 and 3, 3 and 3, 4 and 5, but 4 breaks down to 2 and 2. So there's nothing they had in common. So then they broke it down to 3 A's and 4 B's, 6 A's, 3 B's, just like we did, and figured out what they had in common, and then pulled it out to the greatest common factors. Then they multiply it back together to make sure it equals what it started with. When they multiply those back into there, you get what you started with. And so here is the factored version, and they show how you're subtracting to get it, like I was talking about. So see, factor completely. So this one, they have V's and W's. So 12VW to the fourth plus 28V to the third, W to the sixth, plus 4V to the seventh, W to the eighth. So the first thing they want to look at is the 12, the 28, and the 4. And so they make a list of the factors. Here's the numbers you can multiply to get 12. 1 and 12, 2 and 6, 3 and 4. 28 can be 1 times 28, 2 times 14, or 4 times 7. Factors of 4 is just 1 times 4, or 2 times 2. So if you look at it, the largest number that go in all 3 of these factors is they all have a 4. There's a 4, there's a 4, there's a 4. It's not going to highlight this 4. There it is. There's the 4. So you can pull the 4 out of all of them because it's 4 times 3, 4 times 7, and 4 times 1. So the first thing they did is factor a 4 out to lower the coefficients. Then they look at the variables. They all have V's and W's. See, that it has a V to the third, and a V to the seventh. So you can pull 1 V out of each one. This has a W to the fourth, a W to the sixth, and a W to the eighth. So they all have at least 4 W's that you could pull out. 4V W to the fourth, and then you write what's left in there. So again, you can go through their examples. We're going to do some more examples. There's 9 pages to this, so we're going to go on because you can review this on your own. Then they multiply it back together to make sure it works. But let's work this next one on paper again. 2x squared minus 26x plus 44. So again, we start with the numbers 2, 26, and 44. Well, do they all have anything in common? Well, yeah, they're all evenly divided by 2, right? 2 is the only factors of 1 and 2, so we don't have to really write out all these lists because we know 2 is the only number we have a chance. And these are all even numbers. They will divide by 2. So we know we can first off pull a 2 out. which leaves this as x squared minus 13x plus 22. All right, that's just dividing every term by 2 and pulling it out front. Greatest common factor. Now we have a quadratic equation, so we can factor this further. So let's see if this is a nice quadratic that factors evenly, and we don't have to use the quadratic formula or anything. So remember, when factoring, we're trying to find two binomials that would multiply together to be this trinomial. And x times x would be x squared. The first term is going to be, since this is just an x squared with no coefficient, we was able to take the coefficient out. That helped a lot. X squared means this is going to be an x times an x. But we need to know what the second number is going to be. Well, we can find that by looking at these two terms. The second numbers should multiply together to be this number. Multiply together to be 22. And they should add together to be this number, negative 13. So they should add to be that and multiply to be that. So we got to look at the factors of 22 to figure that out. Now, if we're looking at the factors of 22, this is a positive number. So we know that we're going to be multiplying either two positive numbers or two negative numbers. It's not going to be a positive and negative because we're ending up with a positive number. And we know when we add them together, it's going to be a negative. So that tells us what are the negative factors of 22. Well, 22 does not have many factors. The only way you can get 22 is 1 times 22, or negative 1 times negative 22, or 2 times 11, negative 2, negative 11. That's it, right? There's no other numbers we can multiply together to be that. And since we know they have to add together, we don't even need to look at the positive ones because they're not going to add together to be a negative number. So that leaves us with these, negative 1 and negative 22, which adds together to be negative 23, or negative 2 and negative 11, which add together to be negative 13. So that's the ones we want. We want negative 2 and negative 11 because they multiply together to be 22 and add together to be negative 13. So negative 2, negative 11. Those are the factors of this quadratic equation. It's like, do we know that for sure? Well, we can multiply them back together to check. 2x minus 2 times x minus 11. So when we have three things multiplied together, it doesn't matter which ones you multiply together first, right? If we have 2 times 3 times 4, we can either take 2 times 3, which is 6, times 4, or we could have done these together first. 2 times 3 times 4 is 12. It didn't matter which ones we did first, this or this or this and this, because this equals 24 and this equals 24, because multiplication works that way. Doesn't matter which ones we multiply first. So I'm going to multiply the simplest thing first. I'm just going to take the 2 and multiply it times the first term. So that's 2x minus 4. And then we'll multiply that times x minus 11. 2x times x is 2x squared. 2x times negative 11 is negative 22x. So that's distributing the first term. Now let's distribute the second term. Negative 4 times x is negative 4x. Negative 4 times negative 11 is plus 44. These are like terms, so we can combine those. Negative 22x minus negative 4x, negative 26x, and then plus 44. Is that what we started with? It is. So these are confirmed to be the factors of this, factoring quadratics. If we would have tried to factor this to start with, it's a whole big mess. It's like, oh, this is a 2x squared, so it's not x times x, it's 2x times something. Well, we'd had to factor it like this. So pulling out the greatest common factor makes this a lot simpler to learn how to factor the quadratic equation. So it talks about, same thing, factor out the greatest common factor. Did it have one? Yes, 2. So we pulled out the 2. Then we had to determine, okay, how do we factor the x squared minus 13x plus 22? So it's going to be an x times an x to get the x squared, but what is going to be the factors of the 22? Again, they looked at 1 times 22 or negative 1 times negative 22, all 4 of those. And the only one that added together properly is the negative 2 and negative 11. So that gave them those factors, negative 2 and negative 11. And then they checked it by multiplying it back together. And they multiplied the 2 binomials together first. They kept the 2 until last. See, they multiplied them together and got x squared minus 13x plus 22, and then multiplied the 2. Like I said, we could do that either way. I multiplied the 2 first. So it doesn't matter which way you prefer. Let's go to page 2. That's a lot on page 1. And we spent like half an hour on page 1. Difference of squares. All right, here's one of those cheat codes I was talking about. So we're gonna walk through this and learn what we're talking about with difference of squares. So let's look at some examples of pairs of binomials. All right, I'm going to do these on paper just so we have something to look at that might make some sense about what we're talking about with differences of squares. So let me write these down. So let's multiply these together. If we have g plus 9 and g minus 9, g plus 9, g minus 9, g times g. So distributing, we got g squared. Then g times negative 9 is negative 9g. Okay, then we distribute the 9 to both of those. 9 times g is positive 9g. 9 times negative 9 is negative 81. Okay, these cancel out. Look, we got negative 9g, positive 9g. So if we add 9g to negative 9, all that's left is g squared minus 81. That's the answer when you multiply these two binomials together. Let's try this one. 5g plus 8, 5g minus 8. 5g times 5g, 25g squared. 5g times negative 8, 5 times negative 8 is negative 40g. Then positive 8 times 5g is a positive 40g. 8 times negative 8, negative 64. The middle term again cancels out. We got negative 40g plus 40g. So this equals 25g squared minus 64. Okay, I'm starting to see a pattern. Let's just say we have a plus b times a minus b. A and b can be anything, right? Just two variables. A plus b, a minus b. A times a is a squared. A times negative b is negative ab. Now let's distribute the b. B times a is ab. B times negative b is negative b squared. Negative ab plus ab cancels each other out. A squared minus b squared. Oh, this is a shortcut. If we have a as the first term in both binomials, we're going to end up with a squared. If we have b as the second term, we're going to end up with b squared. And if we have a positive and a negative, we're going to end up with a negative in the middle. Positive, negative, negative. So that means if I'm multiplying, this is our cheat code right here. If I'm multiplying x plus 3 times x minus 3, I can just write down the answer of x squared minus 9. I don't have to do all this work. Because if I recognize the pattern, oh, these are the same and these are the same, and there's a positive and a negative, the answer is going to be the first one squared and the second one squared with a minus in the middle. X squared, 3 squared with a minus. This is called the difference of squares. Difference of squares. What's difference means? When we subtract, we're taking the difference. What's the difference between 7 and 5? Well, 7 minus 5 is 2. The difference is 2. Difference means subtract. These are both squares because it's a squared and b squared. So we're finding the difference between the two squares. What's a squared minus b squared? Difference of squares. That's where this term comes from. Difference of squares. So if you recognize what's going on, you can go this way. Likewise, let's say we have this 4x squared minus 25. And I ask you to factor this. Factor this. What's the factors? If you recognize that these are both squares, you can just write down the factors. So what multiplies times itself to be 4x squared? Well, 4 is 2 times 2. X squared is x times x. 2x times 2x is 4x squared. This is a perfect square. This is a perfect square because it's 5 times 5. So that means one of these be positive, one of these be negative. Those are the factors of that. Using difference of squares. Using difference of squares, I can factor this like that without any other work. It's a cheat code. So this is what I'd probably have in my notes is the A and the B, because A could be A is 2x and B is 5, or A is x, B is 3, A is 5g, B is 8, A is g, B is 9. It can be whatever. A plus B, A minus B is A squared minus B squared. The hard part is recognizing that both of these are squares. They are both something squared. So it's 2x squared and 5 squared. That's 2x squared. That's 5 squared. Difference of squares. It's a cheat code. It's a fast way to factor or a fast way to multiply these together. But you got to be able to recognize what a square is. That is a number squared. And we're going to do an exercise in just a few minutes here to where we're going to see if we can recognize these. Because recognizing that is quicker if you I mean, we can still do it the old fashioned way. We can multiply, we can multiply x times x and x times negative 3 and 3 times x and 3 times negative 3 and write all those out and then figure out what we can combine as like terms and cancel out and get to here. But if we recognize, hey, this is a difference of squares things, we can just jump straight to the answer. Or other way around. We can try to factor all this, but difference of squares saves us time. So they're doing those two, the g plus 9, g minus 9, to show it's g squared minus 81. The 5g plus 8, 5g minus 8, to show it's 25g squared minus 64. Then they start looking at what does that mean? So we've already kind of done that on paper, so I'm not going to spend a lot of time with that. But here it is with the a's and b's, a plus b, a minus b, where it's a squared minus b squared. So the square root of each perfect square is a and b, a squared and b squared. And they give you, in case you have trouble recognizing squares, if that's a problem for you, if you don't know your multiplication tables really good, maybe you want to put this in your notes. These are all perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144. That's the numbers 1 through 12 as a square. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. So you got to be able to recognize those. If you don't recognize that 64 is a perfect square, you're going to miss that. Oh, I didn't recognize it was a difference of squares. I could have just used the shortcut. Yeah, 64 is 8 times 8. That's a perfect square. And this is right here in your lesson on page 2. A list of commonly used perfect squares. When you click on that, it shows you the first 12. So if that helps you, put that in your notes. Have those written down. If you already recognize those, you know your multiplication table so well that immediately when you see 36, I know that's 6 squared. When I see 121, I know that's 11 squared. Then you're good. You probably don't need that in your notes. But it does help to find those perfect squares if you know these first 12 at least. Maybe a few more, maybe the first 15, but the first 12 is really good. Okay, here is that activity I said we're going to do. In fact, I'm going to make this a little bigger on the screen. All right, I'm going to open up the chat so that way I know people are awake. We want to look at each one of these and figure out, is this a difference of squares problem or is it not? So all you're putting on the chat, yes or no, Y or N. That's all you have to put, yes or no. So this first one, let's start with this one right here. 81 minus 25t squared. Is that just an expression or is that actually a difference of squares? 81, is that a perfect square? 25t squared, is that a perfect square? And are we subtracting those? Is that a difference? Olivia says this is a difference of squares. Yes, Breland said yes, it is. Yes. All right, everyone thinks it is. Good, good. Some people get confused and saying, well, isn't the t squared has to be the first term. No, it doesn't. We're subtracting the t squared. The only thing we have to look at is, are they both perfect squares? Yeah, this is 9 times 9, and this is 5t times 5t. They are both perfect squares. Good job. That was a difference of squares. How about this one? Again, we have the number first and the exponent with the variable second, but that shouldn't make a difference. Oh, Breland says no. No, Truman's no. People are saying no, this is not a difference of squares. Nope. Why is it not a difference of squares? Isn't 64 a square? Yeah, 64 is a square, right? That's 8 times 8. That's one of the ones I highlighted a minute ago. 9r squared. Isn't that 3r? See, Olivia's got it. It is 3r times 3r, but this is not a difference. This is a sum of squares. When you add things together, you get a sum. So this is a sum of squares, not a difference of squares. So these are both perfect squares, but we're not subtracting. Good eye there, you guys. You guys were not going to be fooled by that. How about this one? 9g squared minus 12. And you guys are more awake than my class yesterday that was after lunch. After lunch, Algebra 2, they thought the last one was a difference of squares, and they thought this one was a difference of squares. And I was down them both times. No, it's not. This is not a difference of squares because of 12. If we go up to our list again, 12 is in between 9 and 16. It's not a perfect square. So that one doesn't work because the 12 is not a square. How about 4t squared minus 49s squared? Oh, two variables, but are they perfect squares? Truman says, yep, not a problem. We can do that. Oh, you guys are going to do well spotting these because you're doing great. You're going to spot these and be able to quickly give answers when you recognize the difference of squares. This is a difference of squares. This is 2t times 2t and 7s times 7s. So that's 2t squared, 7s squared. How about 16h squared minus 1? Is that a difference of squares? Yes, 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 I'm seeing. We have several people convinced that this is a difference of squares. I'm just letting that hang out there. 16h squared. So that is, oh, excuse me, that is 4h times 4h, right? So that is 4h squared. Okay. And 1, yeah, 1 is a square because it's 1 times 1. So that is a difference of squares. Great job. How about 16y squared minus 4x? Oh, I'm seeing quick response on that. Well, 16 is 4 times 4, and y squared is y times y. So 4y, and 4 is a square. It's 2 times 2, but that's just an x. That's not an x squared. So good job. All right. You guys nailed that. So I think you got a good concept of what a difference of square looks like. So with that in mind, let's do this one on paper. I think this would be worth our time. Since you guys are so good at this, is this a difference of squares problem? Oh, well, the first thing you look at is, well, wait a minute, 3 is not a perfect square. I don't know about 363, but I know 3 isn't. But remember, when we factor anything, the first step always, always, always greatest common factor. Ah, greatest common factor. So the factors of 3 are 1 and 3. 363 is divisible by 3 because we can see 3s and 6s. So if we factor out a 3, now we've got d to the 4th minus 363 divided by 3 is 121. Because we multiply 3 times 121, 3 times 1, 3 times 2, 3 times 1, d squared. Oh, that changes the whole problem. We factored out this 3. Is this a difference of squares? D to the 4th, is that a square? Product property says we can add those together if they're the same or different or whatever. D to the 4th is d squared times d squared. So this is it's d squared squared. That's what it is. It's d squared times d squared. So it's d squared squared. So this is a perfect square. How about this? 121 d squared. So this factors to d squared and 11, because that's 121 is 11 squared. D squared and 11, and we make one positive and one negative. That's it. That's what it factors to. Using the difference of squares. You might not have recognized the difference of square problems because you forgot this is the first step. Greatest common factor. Once we factor 3 out, then it becomes a lot clearer. Wait a minute, this is a difference of squares. So it factored real easily. And these do not factor any further, right? This is a difference, and this is a square, but 11 is not. So this is the final square. That's the final factors. That's a good one to look at. Greatest common factor. Don't forget to take greatest common factor first. So they factor out the 3. Oh, and they actually factored out a d squared. Oh, I missed that. I could have taken a d squared out of it. So this would actually factor out to 3d squared. And then it's d squared minus 121. So I missed it because I didn't factor further. So if I factor that out, this is now d plus 11, d minus 11. Oh, see, I didn't factor it far enough. Oh, this would be 11d. That's right, not 11, because this had a d squared. So this would be 11d, which means I could factor for more d's out of there. Factor a d squared out of there. So this actually is the answer. I didn't factor all my d's out. I didn't write it down correctly. But take a 3 out and take a d squared out. And now it's d squared minus 121. Mr. Brock didn't take it far enough. Step 2, d plus 11, d minus 11. And they multiply it all back together to show that it is what it started with. Factor 4d to the 6th minus 1. Okay, that one doesn't have a greatest common factor. 4d to the 6th minus 1. We'll write that over here in our color there. 4d to the 6th minus 1. No greatest common factor because we just have a 1 as the second term. So does this break out into 2? 1 times 1 is 1, right? So that's a 1. 4d to the 6th. Well, that's 2d to the 3rd times 2d to the 3rd. Yeah, that's 2d to the 3rd squared. Because remember, we can add these together. 3 and 3 is 6. Plus 1 minus 1. Factors real nicely there. And it doesn't factor in any farther than that. Let's look at page 3. Perfect square trinomials. Here's the other shortcut we're going to figure out. Whew, so let's look. They want to use these right here. G minus 3 squared. Okay. So here's our other cheat code we're going to learn. Playing with binomials. Squaring. So if we square this, that means that we're actually taking g minus 3 times g minus 3, right? That's what happens when you square something, is you multiply it times itself. This one would be 4g, the g's are getting terrible. 4g plus 11 times 4g plus 11. You multiply it times itself. So what do we get when we square a binomial? G times G. Let's distribute. This is distributed to both terms. G times G is G squared. G times negative 3 is negative 3G. Negative 3 times G, we distribute in these two. And negative 3 times negative 3 is a positive 9. So we have like terms. So this is G squared minus 6G plus 9. And that's what it equals when we multiply that together. G minus 3 times G minus 3. If we do this one, 4G times 4G is 16G squared. 4G times 11, 44G. 11 times 4G, 44G. 11 times 11, 121. Again, like terms, so this equals 16G squared plus 88G plus 121. Again, a pattern is starting to emerge. Let's see if we can figure it out by doing our A's. If we have A plus B squared, and let's also do A minus B squared just to compare them. Just using our standard A and B, could be representing anything. So that's A plus B times A plus B. This one's A minus B times A minus B. And we're trying to recognize a pattern so we can figure out these perfect square trinomials. Trinomial means it has three terms. Tri is three, right? This is a three. This is a perfect square trinomial because I know that I squared a binomial to get it. The factors of it are the same, 4g plus 11, 4g plus 11. So this is a perfect square. It's a lot easier to see that, like, 64 is a perfect square because that's just 8 squared. 64 is a perfect square, but this is also a perfect square because its factors are identical. Just like the factors of 64 are identical, 8 and 8. So let's go back to this. A times A is A squared. A times B is AB. B times A is also AB. And B times B is B squared. So combining our like terms, it's A squared plus, we've got two ABs. 2 times A times B plus B squared. Okay, so that's what A plus B squared equals. A squared plus B squared, and the middle term is a 2AB. What about if it's a negative? A minus B squared. A times A is A squared. A times negative B is minus AB. Negative B times A is minus AB. And negative B times negative B is a positive B squared. So this equals A squared. Negative AB minus another one is negative 2AB plus B squared. Oh, so when we have a minus B squared, A squared, B squared, negative 2AB. This is the pattern. If you have a perfect square trinomial, A plus B squared, you square the first term, you square the last term, and then you multiply terms together and double it, times 2. Multiply it together and double it, times 2. So let's practice one. Let's just say, okay, well, how does that work? If I have a problem that I said, okay, I want you to take x plus 6 squared and give me the answer. Well, you can do all of the work of distributing and all that, writing this out, x plus 6 times x plus 6. But if you recognize, oh, wait, this would be a perfect square trinomial because I'm squaring this binomial. So it follows under this, a plus b. So the answer would be, this would be a, because that's the first term. So that would be x squared. The middle term would be 2 times, multiply those together. Well, if I multiply x and 6 together, that's 6x. But if I double it, it's 12x. And then the last term is just the b squared, 6 squared. That's it. X plus 6 squared is x squared plus 12x plus 36. I just used this shortcut because I recognize, oh, well, this is a perfect square trinomial because I'm squaring this. If I'm squaring this, this is the pattern of the answer. Let's do another one, but let's do a minus this time. So if I'm doing 2x minus 4 squared. Okay, look, that's a minus b squared. That's this pattern. So I need to write the answer like this. So a squared, this is a, so that would be 4x squared, right? 2x times 2x is 4x squared. The middle term to be a negative. If that's a negative, this is a negative. If that's a positive, this is a positive. And I have to multiply the A and B together and double it. Negative 4, well, I don't need the negative. I already have a negative. 4 times 2 is 8, and I double it, so it's 16x. Because 4 times 2x is 8x, and I double it, and it has to be a negative. And then the last term is b squared, so it'd be plus 16. That's the answer. Using our pattern, so this is what you want in your notes right here. How do I make a perfect square trinomial? Now, the harder part is working backwards. All right. So if I say, okay, factor this x squared plus, and I'm going to say, let me think about this. (16x plus 64). Factor that. Well, if you recognize the way to figure it out is, are these both squares? X squared is a square and 64 is a square because it's 8 squared, right? And if I multiply those together and double it, does it equal the middle term? Well, 8 times x is 8x, and that's 16x. That's double. So this must be x plus 8 squared. That's what that factors to. Because if I take the square root of that, equals 8, and then I'm look at that, and if I take it times 2, do I get the 16? Well, I do. And this doesn't have a coefficient, it's just a 1. So that tells me, yes, 8 is the number I'm looking for B. That is B. So A plus B. And x squared is going to be, easy, because that's just going to be the x is the A. Recognizing these is a little harder than difference of squares, but if you get good at it, man, what a quick shortcut to factor this. Boy, that factors so quickly, I can just write the answer and say this is a perfect square trinomial. Special products. So they go through this whole step of multiplying those together like I did. G minus 3 squared, 4g plus 11 squared. And they go through the steps and showing you just, it goes through the same steps I went. They just look at it piece by piece. So if you want to go through that and see how they do it, if you didn't get what I was doing, maybe reading their explanation to help you a little bit better. So let's see if we're as good as this as we were with the difference of squares. Which of these are perfect square trinomials? Yes or no? All right. All right. Are these perfect squares? This is a little trickier because you got a coefficient up here. So you'd have to say, okay, that would be, the square of that, square root. So the first one they throw at is 6a squared minus 24a plus 12. Is this a perfect square trinomial? Well, remember, the first thing you're going to check, Breland says no. The first thing you're going to check is, first of all, these have to be squares. Should be a squared and b squared if this is a perfect square trinomial. What's ours? 6a squared and 12. Yeah, neither one of those, right? Because 6 is not a perfect square. A squared is, but 6 is not, and 12 is not. So that's just a trinomial, not a perfect square trinomial. If it is squares, if I multiply those together and double it, do I get the middle term? So 144r squared plus 24r plus 1. So this has possibilities, right? Because 144r squared, that is a perfect square, right? It's 12r times 12r. That's 12 times 12 is 144. R times r is r squared. So this is 12r squared. 1 is just 1 squared. So that's a perfect square. So if I multiply 12r times 1, 12r times 1, I get 12r. And if I double that, take it times 2, 12r times 12r is 24r. This is a perfect square because this is a squared, this is b squared, and this is 2 times ab, 24r. They say not always easy to recognize. Try this one. 25g squared plus 70g plus 49. What's A? What's B? Here, I'll show you another way to kind of break that down. Okay, if this is our problem, 25AG, 70G, 49, what must A be? If this is squared, which this is a perfect square because 25 is 5 times 5, G squared is G times G, so it must be 5G. So A squared would be 5G squared, which would be 25G squared. 49, B must be 7, because 7 times 7, B squared is 7 squared, which is 49. So if I multiply these together, 7 times 5G would be AB 35G. If I take 35G times 2, does it equal the middle term? It does. This is a perfect square trinomial because I have to look what is A, what is B, and if I multiply those together, 35G times 2, it does equal the middle term. So this is a perfect square trinomial. Okay, try the next one. 16p squared. I'll give you a moment if you want to write that in paper and break it down like I just did. What's A? What's B? And if I multiply them together, do I get the middle term? Okay, I got one yes. Two yeses. I'm going to get you on this one. Oh, Truman says he disagrees. He says, no, I had a few yeses before suddenly I got a no. Truman, why do you say it's not? Can you tell us why that? Because 16p squared, that's what, 4p? See if Truman's typing us an explanation here. Let me put it this way. Truman, you're absolutely correct. Can you tell everyone else why? Oh, Breland's spotting it. Negative 81. What is the square root of negative 81? Well, it's imaginary because it's a negative. That's a negative 81. See, 1 times 1 is 1. 7 times 7 is 49. 9 times 9 is positive 81. Negative 9 times negative 9 is a positive 81. It's a negative 81 that it doesn't work. The numbers are right. If that was a plus 81, this would be a perfect square trinomial because this is 9, this is 4, 9 times 4 is 36, 36 times 2 is 72. It does, the numbers all work except for you can't have a negative. Because that's one thing, if we look at our pattern, This is always positive. Always. Always positive. The only thing that's different is this. And it depends on what the original binomial is. That will be the same. This first sign will match that one. The second one is always a positive. That's a good reminder right there. How about this one? 121s squared plus 110s plus 25. We have to, we don't have much more lesson. Actually, there's a lot of practice problems because we need them. 121s squared. That's 11s squared. 11s. This is 5. 5 times 11s. 5 times 11 is 55. Multiply it times 2, it is 110s. This is a perfect square trinomial. Oh, I'm sorry, perfect square trinomial. X squared plus 4x plus 16. So A is x, B is 4. AB is 4x. Oh, wait, that's supposed to be double. That's supposed to be 8x. This is not a perfect square because it didn't have the 8x. It only had the 4x. And you're supposed to double the AB. All right, maybe a little trickier than the difference of squares. So here they have some to factor completely. Remember, the first thing you have to do, I'm going to move on because we're about out of time. You got to pull that 2 out. After you pull the 2 out, then it works. Another example. Oh, and find the dimensions of the picture. If you want to read through that, it tells you how she found the dimensions of the picture, but we're not going to take the time. I need to see what's on page 4 real quick. The difference of squares binomial. So it's looking back at that. The t to the 8th minus 81 would be, oh, okay, I got you. We do need to do this one more example. I knew there was something else we needed to do. I'm going to make it x to the 8th just because it's easier to work with, but it's the same thing. Oh, 8th, sorry, x to the 8th. X to the 8th minus 81. Are these both squares? Is this a difference of squares? Yes, because this is x to the 4th plus 9 and x to the 4th minus 9. You look at it and it's like, whoa, that was easy. I recognize difference of squares. I'm done. No, you're not done, but yes, you're correct. That was a difference of squares. But if you look at it, what's this? Wait a minute. That's a difference of squares. Oh, I'm not done. This is a sum of squares. I can't do anything with that. But this, I can factor it again. X squared times x squared. And 3 times 3 plus and minus. Oh, see, we have to factor this one again. This one factored. But don't let them fool you. There may be more factoring you can do after the first step. Is this a difference of squares? Well, this is a square, but 3 is a prime number. So this is the final answer for factoring that. This would be partial credit because, yes, this is factoring it, but we're not down to its simplest factor yet. Factor further. So that's the example that they're giving right here. That when you get to t to the 4th plus 9 and t to the 4th minus 9, that's not the final answer because we can break that t to the 4th minus 9 down again. So check and simplify. Check and simplify. They give another example here where you factored a perfect square trinomial. And when they factored it down, it came to d squared minus 4. Well, d squared minus 4, these are both difference of squares, so you had to factor them again. And then you notice you got d plus 2 and d plus 2. So it's d plus 2 squared, d minus 2 squared. All right, let's look. Here's the lesson summary, which goes over everything we just learned. Greatest common factor, that was the first thing we looked at, pulling out a 3 and an r squared. Difference of squares, binomials, difference of squares, perfect square trinomials, and then check your factors to see if they can be factored further. That's what we just looked at. T to the 8th minus 81. Wait a minute, I'm not done. I got to factor it again. So, all right, they gave you 4 pages of practice problems. 4 pages of practice problems. So if there's any of this that looks confusing to you or that you're not sure you totally understand, do practice problems. This one's too easy because they all use different variables. If this is j squared and k, choose the one that has the j squared and the k, the a and the b, the a and the p, the m and the n, the m and the n. They didn't. If they would have done all x's and y's, that'd have been more of a challenge. But activity 2, what is the factored binomials for this? Activity 3, and there's 4 of these problems here. There's 4 there. There's 4 there. See down at the bottom. Once you choose the factors and submit, yay, excellent. You can do another problem. So there's 4 problems. Page 6. This is factor it on your own paper. Here is a trinomial. Then see if you're right. This one, all you can do with this one is factor out the greatest common factor. And there's 9 of those. Factor it. Factor it. Factor it. Factor it. There's some of those perfect squares. Factor the greatest common. And once you factor the greatest common factor out, is it a difference of squares? Is it a perfect square trinomial? Okay, page 7 has 10 problems. Which is this? Is this 5z minus 9 squared? Is it 5z plus 9 squared? Remember, all you have to do is look at the sign of this one. That's the negative one. Go to problem 2. And page 8. Which of these is the factors of that? 10 problems. So they give you lots and lots of practice because these can be tricky to recognize. So they want you to have enough practice to where this gets easy. So it's worth your time to go through these practice problems. All right, now let's look at our assignment for the week. Factor completely. Factor completely. Oh, look at that one. Lots of exponents. Which of the following is a factor? So you have to factor that, and then one of the factors is listed here. Which one? Probably not x to the third, because there's only one x to the third in the whole problem. You can't factor an x to the third out of those. So that one's probably wrong. But one of the factors of this is what? Factor this completely. Factor this completely. Factor this completely. One of the factors is one of these. One of the factors is one of these. And what's the completely factored form of d to the 4th minus 81? So 10 problems dealing with a whole lot of different stuff. Yeah, I know I've done that. Whole lot of different types of factoring, but these are like learning shortcuts to help because we're dealing with quadratics, and if we can recognize shortcuts like some of these difference of squares, that's going to help us save a lot of time later when we're getting these problems. It's like, oh wait, I remember that from the first lesson. That was difference of squares. So that's the answer right there. Yay! So yes, this is one where it's definitely worth your time to do practice problems in the lesson because it'll give you the answer. It'll tell you when you're right or wrong. And if you've got difference of squares down, you do some practice problems like, oh, there's no problem. Maybe I don't have to do all the practice problems because I'm not missing those. I nail those. Now, this perfect square trinomial, okay, that's a little trickier. That one's kind of getting me. That's trickier. I better do it for more practice problems. And of course, if you struggle with any of it, this is a B Day Friday. I'll be here Thursday and Friday this week. So you can come get help. If your grade's below 70, you need to be in here anyway. So might as well get some stuff done while we're here. So Okay, guys, I'll figure out our schedule going forward because this took a lot of time, and I think next week's is not going to be real quick and easy either. So I can't just move it to next week and do 3 lessons. We're not doing that. So I'll figure that out. You guys have a great week. Have fun with your shortcuts, your cheat codes, whatever you want to call them. And we'll catch you next time.